So hello everyone, welcome all to Physics with H0X. And in this video we will discuss about the first chapter of Verma. And let's begin. So here is our exercise, and the first question is find the dimension of linear momentum, frequency and pressure. So we know the formula for linear momentum, that is mass into velocity, and we know the dimension of mass, that is m1, and for velocity this is l1 t minus 1. So the dimension of linear momentum will be m1 l1 t minus 1. And then frequency, so we know the formula for frequency is 1 by time, and so here the dimension will be t minus 1. Then pressure, so the formula is force per unit area, and we know force is mass into acceleration, and for unit area that is area. So here the dimension will be m l1 t minus 2 divided by l2, so it will be m l minus 1 t minus 2. So the pressure the dimension of pressure is m1 l minus 1 t minus 2. Then find the dimension of angular speed omega, angular acceleration alpha, torque and the moment of inertia. And some of the equations involving these quantities are given as omega is equal to theta 2 minus theta 1 by t2 minus t1, then alpha is equal to omega 2 minus omega 1 by t2 minus t1, and here gamma is equal to f dot r, and I, that is moment of inertia, is equal to m r square. So the symbol have standard meanings that it always poses. So first we will find out the dimension of angular speed, and here the formula given as theta 2 minus theta 1 divided by t2 minus t1. So here theta is the angle and t is the time. So here because the theta doesn't have any dimension, so the angular speed will be 1 by t, and the dimension of it will be t minus 1. Then angular acceleration, and here it has been given that alpha is equal to omega 2 minus omega 1 by t2 minus t1. So from the above question we have find out that the dimension of angular speed is t minus 1. So here by putting this we will get the dimension of angular acceleration at t minus 2. Then torque, that is tau is equal to I into alpha. So here it has been given that I is equal to mr square. So by putting it in this equation we will get it as mr square dot omega 2 minus omega 1 by t2 minus t1. So by putting all the dimension of given quantity we will get the dimension of torque h m1 l2 t minus 2. Then moment of inertia, that is I is equal to mr square, where m is the mass and r is the distance. So here the dimension of moment of inertia will be m1 l2. Then find dimension of electric field, magnetic field and magnetic permeability mu naught. And the relevant equations are F is equal to QE. Here F is the force, Q is the charge and E is the electric field. Then F is equal to QVB. Here F is the force, Q is the charge, B is the velocity and B is the magnetic field. And then B is equal to mu naught I by 2 pi A. Here mu naught is the magnetic permeability, I is the current and A is the distance. So where F is the force, Q is charge, V is speed, I is current and A is a distance. And we have to find out the first quantity, that is electric field E is equal to F by Q from this equation, and we will get the dimension H m1 l1 t minus 1 and I minus 1, because we know that charge Q is given as IT, or we know that I is equal to Q by T. So by putting the equation here we will get the dimension of electric field as m1 l1 t minus 1 I minus 1. And just like that magnetic field B is equal to F by QB from this equation, and here the dimension will be m1 t minus 2 and I minus 1. Then magnetic permeability, that is mu naught is equal to 2 pi AB by I from this equation, and here the formula for, the dimension of magnetic permeability will be m1 l1 t minus 2 I minus 2. Then find the dimension of electric dipole moment P and magnetic dipole moment M. The defining equations are P is equal to Q dot D and M is equal to IA, where D is the distance, A is the area, Q is the charge and I is the current. So first of all we have to calculate the dimension of electric dipole moment, that is P is given as Q into D, where Q is the charge and D is the distance. So we know the formula for Q, that is IT. So by putting the dimension of IT here, that is I1 T1 and D is the distance, so here the dimension will be L1 and the dimension of electric dipole moment will be L1 T1 I1. Then magnetic dipole moment M is equal to I dot A. Here I is the current and A is the area. So we know the dimension of area, that is L2, and for I this is I. So here the dimension will be L2 I1. Then find the dimension of Planck's constant h from the equation E is equal to h nu, where E is the energy and nu is the frequency. So we know the equation E is equal to h nu, and from here we'll get that h will be equal to E by nu, where nu is the frequency and E is the energy. So the dimension of h will be the dimension of E divided by the dimension of nu. And we know the dimension of energy is equal to m1 L2 t minus 2 and of frequency is t minus 2. So from here we'll get that the dimension of h will be m1 L2 t minus 1. Then find the dimension of the specific heat capacity C, the coefficient of linear expansion alpha and the gas constant R. And here it has been given that some of the equations involving these equations are Q is equal to mc T2 minus T1, LT is equal to L0 1 plus alpha T2 minus T1 and PV is equal to nRT. So first we will calculate the specific heat capacity, that is here it has been given that Q is equal to mc T2 minus T1. So first of all we will see that what is these terms are. So Q is the heat, that is which has the dimension equal to work done. Here M is the mass, C is the heat capacity and T2 and T1 are the temperature. So from this equation we'll get that C is equal to Q by M T2 minus T1. So because the Q possesses the dimension of work done, we know the dimension of work done as M1 L2 T minus 2 divided by the dimension of M is M and the dimension of T2 minus T1, that is the temperature, is K. So here the heat capacity has the dimension L2 T minus 2 K minus 1. Then the dimension of coefficient of the linear expansion alpha will be. So here in the equation given H, LT is equal to L0 1 plus alpha T2 minus T1. So here LT and L0 as the latent heat, alpha is the coefficient of linear expansion, T2 and T1 are the temperature. So from this equation we'll get that alpha will be equal to LT by L0 minus 1 divided by T2 minus T1. So from here we can get that the dimension of LT and the dimension of L0 will cancel out each other. So here it will be 1 divided by the dimension of temperature, each K. So the dimension of coefficient of linear expansion will be K minus 1. Then the dimension of gas constant R will be, and here the equation given is PV is equal to nRT. Here P is the pressure, V is the volume, N is the number of moles, R is the gas constant and T is the temperature. So from here we'll get that R will be equal to PV by NT. And we know the dimension of P, that is pressure, is M1 L minus 1 T minus 2 and the dimension of volume is L3. Then the dimension of N, that is number of moles each mole, and the dimension of T, that is temperature, is K. So here we can get that the dimension of a gas constant will be m1 l2 t minus 2 k minus 1 mole inverse. Then, taking force, length and time to be the fundamental quantities, find the dimensions of density, pressure, momentum and energy. So here we have to find out the dimension of all this quantity in terms of force, length and time. So let's see. And first of all, we will calculate the dimension of density. We know the formula for it is mass per unit volume, that is m by l cube. So by multiplying and dividing L by T square, we can get it as m by L cube, sorry 1 by L cube into m into 1 by T square into T square by L. So m L by T square can be written as F, and so the equation will be F into T2 by L4. And because we have to find out the dimension in terms of force, length and time here, so we can get that the dimension of rho will be equal to rho, which is density, is equal to F L to the power minus 4 and T2. Then pressure. We know the formula for pressure is force per area. So directly we can find the dimension H, F, L, T minus 2. Then momentum, we know F dot T, that is Ft, and for energy this will be F dot L, and the dimension will be Fl. Then suppose the acceleration due to gravity at a distance is 10 meter per second square. Find its value in centimeter per minute square. So here it has been given that the gravity is 10 meter per second square, and we have to find out its in terms of centimeter per minute square. So we know the value of 1 meter in terms of centimeter is 100 centimeter, that is 1 meter is equal to 100 centimeter, and 1 minute is equal to 60 seconds. So by putting the value here, 10 meter per second square will be given, written as 10 into 100 cm divided by 1 by 60 square minute square. So the final result will be coming out to be 36 into 10 to the power 5 centimeter per minute square. Then the average speed of a snail is 0.020 miles per hour, and that of a leopard is 70 miles per hour. Convert these speeds in SI unit. So we have to convert it in terms of meter per second. So the average speed of snail is given as 0.020 miles per hour, and in SI unit, that is we have to convert it into meter per second. So we know the value of 1 mile in terms of meter is 1609 meter, and 1 hour is equal to 3600 second. So by putting the value here, we can find the average speed of snail in terms of SI unit will be 8.9 into 10 to the power minus 3 meter per second, that is equal to 0.0089 meter per second. And similarly, the average speed of leopard is 70 miles per hour. So in terms of SI unit, this will be 31.28 meter per second, or approximately 31 meter per second. And then the height of mercury column in a barometer in Kolkata laboratory was recorded to be 75 centimeter. Calculate this pressure in SI and CGS units using the following data. Specific gravity of mercury is 13.6. Density of water is 10 to the power 3 kg per meter cube. G is equal to 9.8 meter per second square, that is the gravity at Kolkata. And here also it has been given that pressure is equal to H rho G in usual symbol. So we know the formula for rho, that is equal to specific gravity of mercury into density of water, and is equal to 13.6 into 10 to the power 3 kg per meter cube as the given data here. And the H value is 75 centimeter as given. and we can write it as 75 into 10 to the power minus 2 meter, because we know that 1 meter is equal to 100 centimeter, and the gravity G is equal to 9.8 meter per second square. So first we will find the value in terms of SI unit. So by putting all the value here, we can find the final result H 9960 kg per meter into second square, and this is nearly equal to 10 into 10 to the power 4 kg per meter into second square, or 10 into 10 to the power 4 Newton per meter square. So this is in SI unit. So when we will calculate it in CGS unit, we will find out it as 10 into 10 to the power 4. In case of kg, we can write it as 1000 gram, because we know that 1 kg is equal to 1000 gram. And in case of meter into second square, we can write it as 100 centimeter into second square, because we know that 1 meter is equal to 100 centimeter. And here we can find the final result as 10 into 10 to the power 5 gram per centimeter into second square, that is equal to 10 into 10 to the power 5 dyne by centimeter square, because we know that pressure can be written as force per unit area, and the unit can be equal to Newton per meter square in SI unit and 9 percentage of meter square in CGS unit. So I hope you all enjoy this session. So for more videos, please do like, share and subscribe. Thank you.